Hello everyone, I'm Kang. I'm happy to be here to present our paper, and the title is Towards Sentence Level Inference Attack Against Pre-trained Language Models. Here is some context. We all know that transformer-based models have fundamentally changed the NLP domains, and so far there are more than 40,000 models hosted by the Hugging Face website. Even though language models have huge potentials, their privacy risks are still concerning and under-investigated. This paper mainly focuses on the privacy leakage from the embeddings. Let's think about this setting that can happen in real life. There is an organization X, which if you can think it as a hospital, they might hold some private data like patient's record. If they want to develop some downstream tasks based on their data, they can choose to collaborate with the service provider. They may share the embeddings generated by some language model with this Y, and they think the embeddings are encrypted and safe, but this is not the truth. Y can also perform inversion attack on the embeddings and infer the sensitive information from the data. The thing is, previous work have made some assumptions on the adversary. For example, they assumed the adversary has some level of knowledge of the data. They know what kind of sensitive keywords are there. And based on that, they can train a binary classifier for each keyword they know and to infer the existence of that keyword in the embedding. Obviously, this method the cost is linearly correlated with the number of keywords. On our hand, we present a more powerful attack where our adversary doesn't need to know anything about the target private data. Here is just a more detailed framework. Let's say this hospital holding the private EHR dataset, and they are collaborating with this adversary. They share some private embeddings with this adversary too. On the other hand, this adversary also has access to a public EHR dataset, which he or she can leverage to train adversarial decoder to perform embedding inversion. And it's clear that this adversarial decoder can be easily applied to the private embeddings and infer information from there. Here are some quick definitions. The first is the sentence embedding. Obviously, a sentence has to be based on a vocabulary V, and it's made of all the token or word belongs to that vocabulary. Here we define a mapping from the sentence to the vector space or the embedding space. We can think of F as the language model here. The other thing is the decoder. Our adversarial decoder simply inherits the architecture of the transformer decoder. And the same, it also works in an autoregressive way. Here is our threat model. The adversary has access to the pre-trained language model as a black box. Secondly, the adversary has a set of embeddings from a private dataset, but they do not know the exact information in it. Finally, the adversary also has access to a public dataset belonging to the same domain, but it does not necessarily have the same distribution. We have defined two types of tags in our experiments. The first one is the keyword inference, which is also explored in the previous work. However, we have made it more general by introducing this K, which is the rule of keywords. We don't invent it, we just use some established knowledge. And the key idea of the keyword inference is find the relation between the output of the attack model A and also the ground truth provided by this row K. As for the sentence inference, it's more intuitive. Say we perform the reconstruction embedding a couple of times to get a set of candidates. Let's say R is the number, and we pick a phi, which is a similarity matrix. we find the best match S star among the pool by comparing S with each SI. Here's a quick, simple pipeline for the keyword inference attack. Let's say we have the sentence embedding and we query the adversarial encoder 10 times, generate 10 sentences. After that, we will count the words and eliminate stop words, followed by sorting by frequency to get a list of words. Finally, for the sake of efficiency, you only keep top keywords and we will check if the keywords exist there. And this pipeline also works for sentence inference. We just need to skip the word counting steps. And we have explored two attack settings. The first one is white box, which is private dataset and the public dataset share the same distribution, which means they may be both subsets of a larger dataset. As for the black box setting, which is more realistic, private dataset and public dataset will have different distributions, which means they come from different datasets. And here is the datasets and keyword role that we have used. We consider two domains of data, which is airline and medical. There are two airline datasets, Skytrax and Twitter US. They are all airline reviews. And the keyword role we relied on is the external dataset called World Cities, and which contains over 900 city names that we use as keywords. As for the medical domain, there are CMS and MT. They are all medical transcriptions. As for the keyword role, we refer to the pre-trained spacing NR model to annotate all the medical keywords. Here are some baselines. Note that the decision tree KNN and DNN, they are all classifiers. So they only work for the keyword inference and they cannot generate sentence actually. Then there is this gradient-based embedding inversion. This is a method essentially trying to linear mapping from the embedding space to the token space, but they use a shallow network without considering the context information in the sentence. So this is just the one-to-one mapping. As for our decoder, we have prepared two versions of decoders, which is vanilla at pre-trained. This is due to we prepared two versions of the dataset for each dataset we use. The first version is just a whole dataset. The second version is a subset that after filtering out all the samples doesn't contain any keywords. So the vanilla version is trained on the subset, while the pre-trained version is first pre-trained on the whole dataset and then fine-tuning on the subset to be familiar with the keywords. Here are the evaluation matrix for the keyword inference. We care both the total count of the keywords as well as the unique number, the number of the unique keywords. As for the sentence inference, there is cosine similarity, and we also consider the classic Lu and Rock score. The final and also important one is the word order similarity. So let's look at the results for the keyword inference. First, if we just look at the white box attack in general, we can see actually all the models are doing pretty well, especially for the DNN. They are having really high number on both count and unique matrix. And our pre-trained decoder is actually only slightly better than this method. But however, the things are different for the black box setting. Our decoder tends to be more robust, and it's pretty obvious on the Twitter dataset that every other baseline have 0 counts or unique, and our model is actually working somehow. This is the result for sentence inference. The baseline gradient inversion is actually suffering on almost all the cases because they really don't consider the contextual information during the decoding stage. And the truth is, when we are dealing with language model, almost all their embeddings are contextual, which means the same word if we put them in different contexts, they will be mapped into different embeddings. And that's what makes a difference here. Here are some qualitative examples from the sentence reconstruction. As you can see, although the decoder couldn't get every word correctly, but it largely prefers the word order. And also, therefore, the adversary can actually infer a lot of information related to the original text. Now let's wrap it up. First, we admit that the reconstruction from embedding is hard and it's contextual, and also the embedding space is pretty large. And there are some tips for improve the inversion attack, such as pre-train the decoder on larger corpus or upgrade the decoder architecture for newer decoder model, as well as improve the quality of decoding through some like plug and play methods. And that will be all. I will be happy to take questions from here.